EC111 Lecture 10 Set 4 Memory Arrays. There are different options in terms of the technology inside FPGA, how we are going to implement the memory element. We could have flip-flops that are inside the LUTs, and they typically have a little bit more complex structure, as you can see here. For example, here a D flip-flop structure is shown. It has 6 NAND gates, and each of the NAND gates has about typically 4 transistors, so it's about 24 transistors. The SRAM cell, the basic one, as you could see here, has about 6 transistors, and the basic DRAM cell is typically only 1 transistor. So it's in the figure you could see that there's a 1 transistor and 1 capacitance, but the capacitance is usually the gate capacitance, the drain capacitance for the transistor. So it's actually only 1 transistor per cell. So as you see here, these are different memory options. We have a D flip-flop, which stores 1 bit with about more than 20 transistors. This one is 6 transistor, and the other one is 1 transistor. And if you want a more dense solution, typically we arrange the memory in an array, not just in single flip-flops that are distributed across the design. So these flip-flop based on gates are area and power hungry, which is not desirable. When we have mass storage, we have these arrays of memory. Of course, when we have a register file like a D flip-flop, this is much faster and much more accessible, but of course we pay the overhead for that. The SRAM is a little bit less, not a little bit, much less spacious and power hungry than a flip-flop, but of course it requires a specific set of signals to be asserted. So the controller has to be carefully designed, and these requirements have to be met because we in order for the SRAM data to be stabilized before we assert the different signals, that also is a function of the technology that we have. And in the register files, we could have multiple read ports because we could read from the same content just by having that synchronous assignment, which assigns the value to the to external variables in one cycle. The write is different. We can only write once, but in SRAM, and this can take only 1 clock cycle in a flip-flop, but in SRAM needs more control signals to be adjusted. And the SRAMs usually have common read and write ports, so we have to carefully multiplex them to make sure that we are not overriding into the same location in the memory. The register files have this big overhead of area and power, but they're faster, more flexible. They are not able to store a lot because they're not very compact. The SRAMs, on the other hand, are more compact, and they can be arranged in arrays. Here we have the structure of a SRAM shown. We have the decoder, which decodes the address, and we have both the row decoder that goes to the word line and the column decoder, which is reading the data from the bit lines and then writing it. If you're writing it to a if you're reading it out, it's going to write the values into that circuitry that reads out. Also, we could input the data to the memory and write it to the certain location that we have. The one thing that we need to know about memory is that most of the modern designs have multiple sources of memory. There is no one size fits all solution that we have for the memory, and the reason is that each of these memory elements, they offer different capabilities. Some of them are faster but bigger. Some of them are slower, but they have more. They can handle more data, and because of that, there is this notion of a memory hierarchy. And the memory hierarchy means that we have main memory, which is much larger. It could be even in terms of FPGAs, it could be off chip because we may not be able to handle so much memory on the chip. But we also have the SRAMs that are not as small as DRAMs, but they can offer caches for us, for example, and then we may have registers and multiple even levels of caches that are corresponding to different SRAM with different accessibility. The DRAM architecture, as I have mentioned earlier, it again has the address to read and write, and then it also has a refresh cycle. It has the smallest size, but it also has the dynamic cost of refreshing the memory. And the data is always read and written entire row at a time, and that's also how we read and write to it and how we refresh it. In the next set, we will be looking into memory controller for SRAM.